So you guys are still with me. Let's keep working on your workbook, Lesson 1, Functions Review. And we're going to look at cubic functions now. Cubic functions, another kind of polynomial function, is degree 3. So if you look at the highest exponent on x, you'll see it's a 3, hence the name cubic. So let's try this example. Consider the cubic function with the equation y equals x cubed, yada yada. Use a graphing calculator to sketch the graph of the cubic function. So time to grab the graphing calculator, and I'll get mine as well, and we are going to graph it and find the x-intercepts to the nearest tenth. Okay, so we're going to put that equation in our graphing calculator, which I've already done. X cubed minus 8x squared plus 16x minus 8. And let's take a look. Well, here's the graph showing up here, but we'll hit graph, and there we go. Now, those window settings were still from the previous graph, but as long as we can see our x-intercepts, which is what we're trying to find, we should be okay on this one. So once again, find the x-intercepts. That's like finding the zeros of the function. So we're going to go second calc 0. And we want to be left bound, which would be about in here somewhere. Hit enter. And then we want to be right bound of that far left x-intercept. Hit enter, and for guess, again, we just hit enter. And it looks like our 0 is not a pretty number, but they asked for it to the nearest tenth anyways. So we're going to be writing that down, 0. And since that's a 6, we would round it up to 0.8. Okay, and then we'd go after finding the other two, and I'll do that, and you guys do that, and we'll see if we get the same answer. Okay, so everyone paused the video, and they found the other two x-intercepts, and I'm just going to sketch the graph here. Okay, first x-intercept that we found together was x equals 0.8 to the nearest tenth. The next one over was equal to 2, or if you like, we can go 2.0, but it was exactly 2. And the third and furthest right one was equal to 5.2. So hopefully we got the same values there. Okay, so next type of function we're going to look at is the absolute value function. Now the absolute value function has a basic form of f of x equals absolute value of x, as long as no transformations have been done to it. And it is actually can be broken down into two pieces. It's because it looks like a V. The right half of it, let's do a little sketch of this. The right half of it has the equation y equals x, and the left half has the equation y equals negative x. And it's equal to y equals x for x greater than or equal to 0, a little vertex down here at 0, and negative x for x less than 0. So that's a piecewise function. But for example 5, we're just going to sketch this next graph, f of x equals x minus the absolute value of x minus 2, and then we're going to find the domain and range. So once again, we need a graphing calculator, so let's get those. Okay, so we're going to enter in the graphing calculator the absolute value of x minus 2. Now to find absolute value, you can go to math, and then num, and ABS, that first one there. If you do forget where to find that, you can always go to catalog, second function 0, and scroll down until you find it. Okay, so actually I think it's at the top, but now that bracket acts like the first absolute value sign, so we just need now x, and then minus 2, and the bracket, which is ending the last absolute value sign, and then we'll go zoom standard number 6, set it back to normal, and there we go. There's our graph, and it looks good. We should be able to figure out domain and range, although it would be nice to know, well, that's not going to really affect it if we don't know the x value there, is it? But it is at x equals 2, and you can kind of see that in the graph here, or in the equation of the graph. But let's go back to our page, and we're going to copy that graph down and then find the domain and range. Okay, so our graph looks something like that. And this was equal to 2. Okay, so to determine the domain and range from that, again, domain, all possible x values, and it looks like it goes forever left and right. So I'm going to call the domain x such that x is num in the reals. And it's all real numbers left and right. Okay, now range, it definitely doesn't go below the x-axis. So really the smallest value it looks like we have for y, remember, not x, is 0. So that would mean that y would have to be, well, it's anything above that, so greater than or equal to 0. And then just to define what kind of numbers those are, they're going to be real numbers, all possible numbers, decimals, fractions, you name it. So we tack that on. All right, so those are absolute value functions. We're going to do more with those later in the course. Let's look at radical functions. Radical functions are any function in which the variable is under the radical sign, so the variable is in the radicand, such as this nice basic function. And when that one's graphed, it looks like this. And that anchor point or key point is actually at 0, 0. Okay. Now, we are asked to, on example 6, sketch the radical function g of x equals root 2x minus 1 and find the domain and range. So, once again, we're going to go back to the calculator. Okay, and we're putting in the square root, so second function square root of 2x minus 1. Okay, and the bracket, although your calculator will end those brackets whether you do or not, so it's not totally necessary, but proper form. Okay, and we're still zoom standard. Let's take a look at what that graph looks like. Okay, now this is something that happens that's kind of weird with radical functions. Right in here, the graph is coming down at such a vertical way that the pixels aren't quite showing up. So we could try some different, we could try zoom decimal maybe, see what that looks like. That looks a lot better. Okay, so zoom decimal, we can see this part of the graph that we couldn't see before. So that's actually a good thing. Now, if you look at our table of values, so there's no value for y when x is 0, and there's a value of 1 when x is 1, but somewhere in between there, I think we have a value of 0 for y. So here's probably the best way to do that, is we're pretty sure it comes down to the x-axis, so the smallest possible value, a square root, could be a 0. So what if we let 2x minus 1 algebraically equal to 0 and just solve for x? That's probably the easiest way to get this x value. So back to our paper, and we're going to do that. Okay, so let's just do that. 2x minus 1 equals 0. Solve for x, so add 1 to the other side, and divide both sides by 2. Okay, so we know that that key point is at 1/2 and 0 for y. And there we go. Now that we have that, we can get our domain. So all possible x values, it looks like it really doesn't go left of 1/2, so it's going to be x such that x is greater than or equal to 1/2. And again, it's all real numbers for that line. Range, we don't have anything below the x-axis, but it continues going up from that 0, so y would be greater than or equal to 0. And y is all in the reals. And there we have it. So we're going to continue this lesson with the last part, part 3, for the next page. Thank you.